So, good evening. Can we start? Or should we wait a couple of minutes? Maybe we will wait for 1 2 minutes. After that, we will start.
എങ്ങനെയാണ് കുറച്ച് കാര്യങ്ങൾ നമുക്ക് നോക്കാം. ഞാൻ ഓൾറെഡി ക്ലാസ്സിൽ പറഞ്ഞിരുന്നു തോന്നുന്നു. പിന്നെ കഴിഞ്ഞാൽ
Hello.
ഇതിന്റെ പ്രൊഡക്റ്റ് എന്താണ് നിങ്ങൾ നിങ്ങൾക്ക് അറിയാമോ?
Okay. I will share the slides now. Is the slides visible?
Yes, ma'am.
Okay. So, good evening, all. Week 1 assignment of the NPTEL PMR of tutorials of the course Introductory Organic Chemistry II by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself, Anisha Suresh, PMR of TF for this course from IIT Bombay. So, in this session, we will be discussing as two parts. First, we will have a discussion of the brief summary of whatever was discussed in the week 1 modules. Later, we will be solving few questions from the previous assignment sets. Okay. So, solving this previous assignment sets will be useful for you to solve the assignment 1 that is provided. So, coming to summary of week 1. So in week 1, basically 6 lectures were there, and out of that, 3 were regarding the essentials of NMR spectroscopy, and the remaining 3 were regarding electrophilic aromatic substitution reaction. So coming to essentials of NMR spectroscopy, so in this we have learned regarding the chemical shift, shielding, frequency, etc. So as you can see in this diagram, so this is a 13 NMR spectrum of this compound. So this chemical shift is represented by the symbol delta. And coming towards this end, 0. Like in carbon 13 spectrum, mostly it is covered from 0 to 200 ppm range. So ppm is the unit by which this delta is measured. Okay. So the 0 chemical shift, when it is coming towards 0, the chemical shift will be small, and this is large when it is coming towards 200. And when we are discussing regarding the field, this region, that is the right hand side, is called upfield, and the left hand side is known as downfield. And when we are telling about the frequency, when it is coming towards the right hand side, that is towards 0, the frequency will be lower. And when it is coming towards the left hand side, that is towards 200, the frequency will be higher. And telling about the shielding, this region, starting from 0, the region will be shielded, where the electronic cloud around the nucleus of the atom will be higher, whereas at this side, that is towards 200, it will be deshielded, meaning the electron cloud around the nucleus will be lesser. So hence it can be like at lower frequency only it will be resonating. And now discussing regarding the regions of the proton NMR spectrum. So at what region some of the peaks will be appearing in the proton NMR spectrum, that was discussed. So here this tetramethylsilane, it is used as a reference or standard in the NMR spectroscopy, and it used to appear around 0 ppm in the proton NMR spectra, and the region from 0 to 3. So the region in 0 to 3, so there the saturated hydrocarbons which are not next to an oxygen atom or not next to an electron withdrawing group, they used to appear in this region of 0 to 3. Like if you are considering like CH3 or CH3 CH2, so these protons all used to appear in this region of 0 to 3. And when we consider the region of 3 to 4.5 ppm, so saturated CH3 CH etc that are next to the oxygen atom, like ethers, they used to appear in the region of 3 to 4.5. Okay, like CH3O, CH2, CH3. So this CH2, this CH3, these all appear in the region of 3 to 4.5, and the region 4.5 to 6.5. So normally sp2 carbons, that is protons, used to appear in this region of 4.5 to 6.5, and the region of 6.5 to 8.5, like aromatic protons of the like benzene. If there is benzene and the protons that are present in benzene, it will be coming in the region of 6.5 to 8.5. And when we consider the region of 8.5 to 10.5, the protons of unsaturated carbons that are next to oxygen, such as aldehydes, if we consider aldehydes or acids, so these protons used to appear in the region of 8.5 to 10.5, and it can come beyond 10.5 as well. So this is the regions of the proton NMR spectrum and how the protons are distributed according to their nature in the proton NMR spectrum. This is clear, right? Now coming to the regions of the 13C NMR spectrum. So as you can see in the region, like in the proton NMR spectrum, it is covered from 0 to 10 or 0 to 12 ppm, while in the case of 13C NMR spectrum, it is covering a broader range like 0 to 200 ppm. So the saturated carbon atoms like CH3, CH2, CH etc., they are coming around the region of 0 to 50 ppm. And when we consider like ethers, saturated carbon atoms that are next to oxygen like CH3O, CH2O etc., they will be coming in the region of 100 to 50 ppm. And in this case, the aromatic protons as well as alkenic protons, they are coming in the region of 150 to 100. So there is no much difference as compared to that of the proton NMR spectrum. So the aromatic peaks as well as alkenic peaks used to come in the region of 150 to 100 ppm. And in the case of 13C NMR spectrum, the unsaturated carbon atoms that are present next to an oxygen atom, they will be coming in the region of 200 to 150 ppm. Okay, and the effects of electronegativity was also discussed in the lecture. Like if this is the compound, that is CH3Li, where Li is an less electronegative atom, the electronegativity of lithium is coming around 1. So the proton NMR shift, it is coming around minus 1.94 ppm. As we have seen in the case of tetramethylsilane, the electronegativity of silicon is 1.9, and hence we have chosen it as a standard where it is coming around 0 ppm. And when we have atoms with greater electronegativity, we know the electronegativity of carbon is around 2.5 ppm or 2.4 ppm. So if atoms having greater electronegativity than carbon is present, like nitrogen which is having an electronegativity of 3 ppm, electronegativity of 3. So this protons like CH3 NH2, these CH3 protons will be coming in the region of 2.41. And if we have an oxygen atom that is attached next to the CH3, whose electronegativity is coming around the range of 3.4. So here in the proton NMR spectra, this CH3 will be coming in the region of 3.5. Okay. And if we have fluorine next to CH3, so we know that fluorine is having an higher electronegativity value, that is around 4. And hence the proton NMR shift will also be greater, like the CH3 will be appearing in the region of 4.27. So what we have to conclude from this is that as electronegativity increase, the proton NMR shift or the chemical shift also increases. Okay. So this is the effect of electronegativity on chemical shift. Now coming to the second session, that is electrophilic aromatic substitution reaction. So in this case, three major reactions were discussed. The basics of the electrophilic aromatic substitution were discussed, and apart from that, three main name reactions were discussed. That is Friedel-Crafts alkylation, Friedel-Crafts acylation, and Gattermann-Koch reaction. Okay. So this is the mechanism for Friedel-Crafts alkylation reaction. So when we are having an alkyl chloride in the presence of AlCl3, which is a Lewis acid, it will coordinate with this chlorine, and this group will leave as AlCl4 minus. This will be leaving. So it will result in the formation of a tertiary carbocation and this aromatic ring. So it will go and attack the tertiary carbocation, result in the formation of this intermediate. So here, uh, now the aromaticity of this ring is low, so it will be having a tendency to regain its aromaticity. So some base, if it is present in the media like Cl minus, it can abstract the proton and neutralize this positive charge, resulting in the formation of this product. So what is basically happening? Alkylation on the benzene is happening here. Okay. And in case of Friedel-Crafts acylation reaction, so we are having an acid chloride in the presence of AlCl3. This AlCl3 will coordinate with the chlorine. The lone pairs on oxygen will push, and this AlCl4 minus will be leaving, leading to formation of the acylium ion. So this is the reactive intermediate here. Now the benzene will be going and attacking on this carbon, neutralizing the positive charge on oxygen, resulting in the formation of this intermediate. And now any base can come and abstract this proton, neutralizing this positive. Hello, any doubts? If you are having any doubts, you can stop me in between and ask. Okay, no problem. So the benzene ring will go and attack on this carbon atom of the acylium ion, and it will neutralize a positive charge on this oxygen, resulting in the formation of this intermediate. Now this is a reactive intermediate, as this aromaticity of the ring is lost, and it will have a tendency to regain the aromaticity. So the base or Cl minus can come and attack the proton or abstract the proton, and it will neutralize a positive charge on the aromatic ring, resulting in the formation of this final product. Okay. And coming to Gattermann-Koch reaction, it is also similar to Friedel-Crafts acylation. Here, basically what is happening is formylation reaction. Like aldehyde is adding instead of ketone. So in Gattermann-Koch reaction, these are the reagents like HCl, carbon monoxide, AlCl3, which is used in catalytic amount, and CHCl, which is used as a co-catalyst. So here what will happen, in the presence of HCl, carbon monoxide will lead to formation of acylium ion like this. Now, similar to the Friedel-Crafts acylation reaction, this benzene ring can go and attack on this carbon atom, neutralize the positive charge on the oxygen, resulting in the formation of this intermediate. And this upon abstraction of this proton and neutralizing the positive charge on the ring, result in the formation of this final product. So this is known as Gattermann-Koch reaction. Basically, it is a formylation reaction. Clear?
Yes, ma'am.
Okay.
Yes.
So, for further references, you can follow Claydon Organic Chemistry, Chapter 3 and Chapter 11 for NMR spectroscopy, and Chapter 22 for electrophilic aromatic substitution reaction. Okay, all that were explained in the lectures are clearly mentioned in this book.
Okay, ma'am.
Now, coming to the first question, which of the following have the correct arrow pushing sequence? So, this is an example of nitration reaction, that is an electrophilic aromatic substitution reaction.
Option A.
Okay, option A is the right answer. This is the right arrow pushing mechanism. So we can see how the nitration reaction mechanism is taking place. Okay. So for nitration reaction, this nitronium ion is the reactive intermediate. So how this nitronium ion is forming? So in nitration reaction, we will be using a mixture of nitric acid and sulfuric acid. So this lone pair of oxygen on the nitric acid will abstract the proton from sulfuric acid, resulting in the formation of this intermediate. And upon pushing this lone pair of electron, a water molecule will leave and it will result in the formation of the nitronium ion, which is a reactive intermediate. Now, what will happen? We are having a benzene. So, this double bond can go and attack on the reactive nitronium ion, in like it will go and attack on this nitrogen atom, and this O minus will be forming. So it will result in the formation of this intermediate. And what will happen? This intermediate is very unstable as aromaticity of the benzene ring is lost. So this proton can be abstracted by any conjugate base that is present here. So this proton will be abstracted and it will neutralize the positive charge on the ring, resulting in the formation of nitrobenzene. So this is basically the mechanism for nitration reaction. And as you have said, this is the nitronium ion, and the double bond on the benzene can go and attack on the nitrogen, and this lone pair and this double bond will break and it will push towards the oxygen. So option A is the right answer. This is clear?
Yes, ma'am.
Okay. So if this is clear, we can move to question number 2. So this is question number 2. When benzene and cyclopentene were mixed together in the presence of sulfuric acid, the expected product is
Option number C.
option number C. So let us see what is happening here. So we are having H2SO4 as the reagent. So in the presence of H2SO4, the cyclopentene will lead to formation of this carbocation, which is a secondary carbocation. Then what will happen? The benzene ring will go and attack on that secondary carbocation, resulting in the formation of this intermediate. And since this is a unstable intermediate, the base can abstract the proton. Here HSO4 minus can be the base. It can abstract the proton and it will lead to formation of this final product. Is the mechanism clear? First, we are having a cyclopentene. In the presence of H2SO4, it will lead to formation of this secondary carbocation. Now, the benzene ring can go and attack on that carbocation, resulting in the formation of this intermediate. This is an unstable intermediate as the aromaticity of the benzene ring is lost. So, in any base that is present in the medium, so basically here HSO4 minus will be the conjugate base of H2SO4. It can act as the base and it will abstract this proton and neutralize the positive charge, leading to formation of this final product. So, as you said, this is the right answer. Option C is the right answer. Clear?
Yes, ma'am.
Okay. Now coming to question number 3. The 13C NMR signals are in the following order of chemical shift delta value. So here this is the B carbon, this is the A carbon and this is the C carbon. Okay. So how the 13C NMR signals will be coming for this carbon? So for these carbons, that is A, B and C. We have discussed regarding the range where the carbon signals will be coming depending upon like if it is sp2 sp3 present next to oxygen, present not next to oxygen, like that we have seen. So accordingly you have to find if A equal to B equal to C or A greater than B greater than C, A equal to C greater than B or A greater than B equal to C.
A equal to C greater than B.
A equal to C greater than B. That is right. So we have seen this is alkenic proton. A is alkenic proton and this is aromatic. Sorry. A is alkenic carbon and the C is aromatic carbon. And this is normal sp3, which is not present next to an oxygen atom or something. So this B will be coming in the region of 0 to 50 ppm and A, comma C, it will be coming in the region of 100 to 150 ppm. So we can write like A equal to C and it is greater than B. Okay. So this is the regions that we have seen for saturated carbon atoms like CH3, CH2, CH, etc. So here B is CH2, that is not next to any oxygen atom. So it is coming in the region of 0 to 50 ppm. And saturated carbon atom next to oxygen like CH3O, CH2O, etc. they are coming in the region of 100 to 50 ppm. And unsaturated carbon atoms like C double bond C and aromatic carbons, they are coming in the region of 150 to 100 ppm. And we have seen that the C double bond C aromatic carbons, they are coming in the region of 150 to 100. So this A and C will be coming in this region and here B will be coming in the region of 0 to 50 ppm. So hence we can conclude that A equal to C greater than B will be the right option here. Any doubt?
No, ma'am.
Okay. If there are no doubts, we can move to next question, that is question number 4. So the intermediate formed during Friedel-Crafts acylation reaction is. So they have given three options A, B, C. So out of which is the intermediate that is formed during Friedel-Crafts acylation reaction?
Option A. Sorry, B.
Option B will be the right answer. So we have seen the mechanism for Friedel-Crafts acylation reaction. So we are having an acid chloride In the presence of AlCl3, this will coordinate with AlCl3, and when lone pair on oxygen will be pushing, as you can see here, this AlCl4 minus will be removed, and whatever resulting, that is acylium ion, it is a reactive intermediate for the Friedel-Crafts acylation reaction. So since a lone pair on oxygen is pushing here, a positive charge will be coming on the oxygen atom, and since four bonds are already present, carbon atom will be neutral in this case. Okay, so this is the reactive intermediate for Friedel-Crafts acylation reaction, and after that, normal like any electrophilic aromatic substitution reaction, the benzene ring will be going and attacking on the carbon atom. This positive charge on oxygen will be neutralized, resulting in the formation of this intermediate, and Cl can come and abstract the proton, and it can neutralize the positive charge that is present in the ring, resulting in the formation of the acylated benzene ring. Clear?
Yes, ma'am.
Okay. So option B is the right answer in this case. Everyone is in the same page, right? It is clear for everyone, right? Any doubts? If there are no doubts, we can move to question number 5. 1,3-dibromobutane. One oxygen is extra here. 1,3-dibromobutane has dash number of proton NMR signals. 2. So let me draw the structure of 1,3-dibromobutane. So 1, 2, 3, 4. 4 carbons, it is butane, and bromine. If we number it 1, 2, 3, 4. So here one bromine and here one bromine. I will draw it more clearly. We give numbering 1, 2, 3, 4. Okay, this is the structure of 1,3-dibromobutane. So how many proton NMR signals will be there?
Ma'am, 4.
4 signals will be there, because here here 3, whatever CH3 that is coming here is considered as 1, this CH is considered as 2, this CH2 is considered as the third one, and this CH2 is considered as the fourth one. All these are in different chemical environments, so 4 different signals will be shown in the proton NMR spectra. Okay. So this is the structure of 1,3-dibromobutane, and we can see 4 different signals. I will highlight. This is 1, 2, 3, 4. All these protons will be appearing different as they are in different chemical environments. Clear? So option D will be the right answer, that is 4. Is this question clear?
Yes, ma'am.
Okay. Now coming to question number 6. The product of the following reaction is, so benzene is there and an alkyl chloride is there in the presence of AlCl3. What product you will be getting? They have given 4 options. This is A, B, C and
Option B, ma'am. Right answer.
B.
D is the right answer. So what is happening here? What is the name reaction?
Alkylation.
Friedelkraft.
Yeah. Friedelkraft, alkylation, reaction. So we are having an alkyl chloride and AlCl3. So in the presence of AlCl3, this alkyl chloride will lead to formation of a stable tertiary carbocation, and then the benzene will go and attack on that carbocation, resulting in the formation of the final product. So we can see the mechanism like this. So this is the alkyl chloride in the presence of AlCl3. AlCl3 will coordinate with Cl, and then it will leave as AlCl4 minus. So it will lead to formation of a tertiary carbocation, which is a stable carbocation, and the benzene, it will go and attack on that tertiary carbocation, leading to formation of this intermediate, which is unstable. So the proton will be abstracted by Cl minus, and then it will result in the formation of the final product. Clear? So this is
Yes, ma'am.
Friedelkraft alkylation reaction. So this is the final product that will be forming, that is option B. Okay. Okay. Now coming to question number 7. For the following compound, which of the following statements are true? So here 3 protons are labeled, that is A, B and C. Ortho, meta, para protons are labeled for the cyanobenzene. So they are asking which of the statement is true. The chemical shift of A equal to chemical shift of B. Chemical shift of B equal to chemical shift of C. Chemical shift of A is larger than B, and chemical shift of A, B and C are identical.
Ma'am, option
Chemical shift of A is larger than B.
What could be the reason? Chemical shift of A is larger than B.
It is near to a
Ma'am,
cyano
mesomeric
group.
effect.
Okay. So the presence of the cyano group is somehow influencing this chemical shift difference. Okay, we will see how it is. So as you can see here, because of the presence of the cyano group, the double bond can move in this fashion like resonance. Okay, so a positive charge will be present at the ortho position, and if this again undergo resonance, this double bond will shift here and a positive charge will be present on the para position. And if it is moving, this double bond is moving here, then a positive charge will be present on the ortho position. So at ortho position and para position, positive charge is present. So electron density will be lesser at the ortho position and the para position compared to the meta position. Okay, electron density will be lesser at the ortho and para position compared to the meta position because of this resonance that is taking place as this electron withdrawing cyano group is present. Fine. And if the electron density at a particular carbon or hydrogen is lesser, it will be de-shielded, like its chemical shift will be more compared to the other protons that we have seen, right? Shielded means electron density around the nucleus or atom will be higher. De-shielded means the electron density around the atom or nucleus will be lower compared to the other. Okay, so in this case at ortho and para position, since this positive charge is present, the electron density will be lower. Electron density is lower at ortho and para positions compared to meta position. Okay, so what is the result? Because of this reason, chemical shift at ortho and para, whatever protons will be present, is more compared to proton present at the meta center. Clear?
Yes, ma'am.
So now when we are coming back to our question, so they are asking what is the difference in chemical shift for A, B and C. And these are the options. Chemical shift of A equal to chemical shift of B. That is wrong, because these two will be showing different chemical shift values. And chemical shift of B equal to chemical shift of C, that is also wrong. This will also be showing different chemical shift as the electron density will be different. Chemical shift of A is larger than B. So as you have seen, because of a lesser electron density or the positive charge that is present at A and C, they will have a greater chemical shift, or they are more de-shielded compared to that of this meta position proton B. So the chemical shift of A is larger than B will be the right answer. Okay, is this question clear?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay, okay. So option C is the right answer in this case. Now moving to question number 8. The intermediate that is formed during bromination of benzene is. So three,
All the above.
okay, three are given.
It is a
They are
sigma
asking
complex.
which is the intermediate that is formed in bromination reaction. So the right answer will be all of the above, and we can see why it is. Okay. So as you have seen in electrophilic substitution on benzene, in the presence of bromine and AlCl3, this double bond can attack on this bromine. This AlCl3Br minus will be leaving, and it will result in the formation of this intermediate. Now this can undergo, so this is the reactive intermediate, and this can undergo resonance. Okay, as you can see, instead of Br, you can consider this electrophile E, and this will undergo resonance. Like this, double bond can shift here, neutralizing the positive charge here, and a new positive charge will be generated here. And this double bond can shift here, and a new positive charge will be present here. So at these positions, as you have seen in the previous example, at these ortho and para position, positive charge will be prevalent in electrophilic aromatic substitution reaction. Okay, so all these intermediates will be there. So then a losing of a proton by abstraction by any base can result in the formation of the final product. So all of these three will be the right intermediate for bromination of benzene. So option D will be the right answer in this case. Clear, right?
Yes, ma'am.
Okay. Now coming to question number 9. For the following reaction scheme, identify the reagents.
Ma'am, option C.
Option C.
Option C. Okay. So what is happening here? We are having a benzene. It will undergo a reaction leading to formation of this ethyl phenyl ketone. And that upon undergoing some other reaction, this ketone will be reduced and we will be getting this alkylated benzene. So what is happening here basically?
Friedel-Crafts acylation.
Friedel-Crafts acylation reaction is taking place. So since we are having an ethyl ketone, so we have to use this uh, acid chloride as the starting material. So this acid chloride in the presence of AlCl3, it will form an acylium ion. The benzene will go and attack on that acylium ion, and deprotonation, it will result in the formation of this product. Now for um, reduction of this ketone, we can treat it with zinc amalgam in the presence of HCl, and that will selectively reduce this ketone and give this alkane. Okay, so we can see what is happening. So the mechanism, I think I will draw the mechanism for this. So we are having a benzene and double bondo ethyl, right? So in the presence of AlCl3, this will coordinate with AlCl3, and this oxygen lone pair will be pushed, and AlCl4 minus will be removed, resulting in the formation of triple bond O plus, which is the acylium ion. Now the benzene can go and attack on the acylium ion, resulting in the formation of this reactive intermediate, and then Cl minus that is present in the medium can abstract this proton, and regain the aromaticity, resulting in formation of the final product. So this is Friedel-Crafts acylation reaction. And this ketone can be selectively reduced in the presence of zinc amalgam, leading to formation of this aromatic alkane. Okay, so option C is the right answer. Anyone having any doubt regarding this?
No, ma'am.
Okay, now coming to question number 10. The number of distinct signals in the proton NMR spectrum is
3, ma'am.
Ma'am, 4.
4.
3, ma'am.
3 will be the right answer. Deuterium will be NMR silent. Okay, so we can, this is CH3s. Okay, these are CH3s. And if we consider this molecule is having a plane of symmetry, so this, if we label HA, HB and HC, this HB and HC are in the same chemical environment, as this is having a plane of symmetry, and all these 9 protons, they will be identical. Okay, all these 9 protons, they will be identical. So this is one signal, these two will appear as the second signal, and these 9 protons will appear as the third signal. So total of 3 signals can be found in the proton NMR spectrum. Clear? This
Yes, ma'am.
deuterium is NMR silent, so it will not show any signal in the proton NMR spectrum. So the right answer will be option 3. This is clear?
Yes, ma'am.
Okay. Now coming to question number 11. How many signals would you expect to find in the 1H NMR spectrum of 2-chloropropane?
2 signals.
2 signals. Okay. So first we have to draw the structure of 2-chloropropane. So propane means 1, 2 and 3. 3 carbon will be there, and in the second position chlorine is present. Okay. So here CH3 is there, CH3 is there, and here a CH is there. So this is the structure of 2-chloropropane. And since this molecule is having a plane of symmetry, these, this if we label as A, this as C and this as B, since this molecule is having a plane of symmetry, A is equal to C. So they will appear as a single signal. Okay. Since this molecule is having a plane of symmetry, this A and C, they will be identical to each other and will appear as a single signal in the proton NMR spectrum, and this B, it will be appearing as the second signal. So there will be a total of 2 signals in the case of this 2-chloropropane. Okay.
Yes, ma'am.
So the answer will be option B. So whatever questions we are discussed so far, that is all clear, right?
Yes, ma'am.
Okay. So now moving to the question number 12. Which of the following statements in the context of proton NMR spectroscopy is true? Arene CH chemical shift values are greater than simple alkene CH chemical shift values because of the aromatic ring current. Second option, arene CH chemical shift values are smaller than simple alkene CH chemical shift values because of the aromatic ring current. Arene CH signals are NMR inactive. Arene CH signals are always singlets. So, which of the following statement is true according to proton NMR spectroscopy?
ए होगा
Okay. Option A is the right option. So, here, as we have seen in the case of benzene, if we keep benzene in an electric field, it will have ring currents generated around it such that inside the aromatic ring, this ring current is opposing the applied magnetic field, and the outer protons will be experiencing a reinforcement of the reinforcement because of the ring current that is formed. Okay, when we are keeping this benzene in an applied magnetic field, so a ring current will be formed across this ring, and it will be opposing the applied magnetic field inside the ring, and outside the ring, that is the outside protons, they will be experiencing a reinforcement of the applied magnetic field. Okay, so in this case, it needs lesser frequency to resonate compared to when there is no ring current present. So in the case of arenes, here because of the ring currents, they will require lesser frequency to resonate compared to that of the alkenes. In the case of alkenes, there is no ring current present as in the case of arenes. So here, because of this reason, the chemical shift values of arenes are higher compared to that of the simple alkenes that are present. Okay, and these two statements like arene CH signals are NMR inactive, that is false. Arene CH signals are always singlets, that is false, because arene CH signals can be doublet or triplet depending upon whatever is the neighboring atom that is present. So this coupling everything you will be learning later, but they will not be singlets always. Okay, so here you the basic concept you have to keep in mind is regarding the aromatic ring current. Inside it will be opposing the applied magnetic field. Outside it will be reinforced by the applied magnetic field, and because of that reason, the arene CH chemical shift are always greater than the simple alkene CH shift. Okay.
Ma'am,
Yes.
ma'am, could you please explain it once again?
Like we have seen that if we are keeping a benzene in an applied magnetic field, so it will generate a ring current across the ring, So that ring current will be in such a fashion that inside of the benzene ring, it will be experiencing, like this ring current will be opposing the applied magnetic field. The applied magnetic field direction is in this fashion. So as you can see, this is the ring current. So when it is coming inside the ring, this arrow will be opposing the applied magnetic field. This is the direction of the applied magnetic field. Okay. So when we are keeping a benzene or an aromatic molecule in an applied magnetic field, it will generate a ring current around it in such a way that it will be opposing the applied magnetic field inside the ring, and it will be the applied magnetic it will be reinforcing the applied magnetic field by the outer protons that are present on the ring. Okay. And because of this reason, um, like we need lesser frequency for resonating this protons that are present on the outside of the benzene ring. And it is the reason why the arene CH chemical shift values will be greater than the simple alkene CH chemical shift that present. Clear?
Yes, ma'am.
Okay. So here the correct option will be option A. Whatever questions we have discussed so far is clear, right? No one is having any doubt, right?
Yes, ma'am.
Okay. So we can move to question number 13. What is the value of the chemical shift delta for an absorption of 1800 Hz from tetramethyl TMS using an NMR spectrometer with an operating frequency of 300 MHz? So here we have to calculate the chemical shift. So in the lectures I have discussed the formula for finding the chemical shift. What was it?
Ma'am, I think the answer will be B, 6 ppm.
6 ppm is the right answer. So what is the formula that we have to apply here?
Frequency of resonance divided by operating frequency.
Yeah. So we have to divide the observed frequency by the operating frequency of the instrument. So here the observed frequency is 1800 Hertz and the operating frequency is 300 megahertz. Okay. So chemical shift, which is denoted by delta, equal to frequency observed, which is in hertz.
Ma'am,
Yeah.
why isn't the answer 0? For tetramethylsilane, it should be 0, no?
No, it is
Because,
for not for TMS, from TMS, right?
what, ma'am?
From TMS it is considered. What is the value of the chemical shift delta for an absorption at 1800 Hertz from TMS using an NMR spectrometer with operating frequency of 300 megahertz?
Oh, right.
It
So
is
sorry.
not
Got it.
for TMS.
Got it, ma'am.
With respect to TMS, they are considering. So chemical shift equal to frequency observed in hertz. Then we will be minusing the frequency of the reference. So frequency of the reference will be 0, right, for TMS, divided by operating frequency of the instrument. That will be in megahertz. And since this hertz will cut, and this 10 power 6 will be going like 10 power minus 6, it is unit is coming as ppm. So here the frequency observed is 1800 hertz and the operating frequency they have given is 300 megahertz. So this will be coming like 6 into 10 power minus 6, that is 6 ppm. Okay. Is it clear?
Yes, ma'am.
Okay. So you have to memorize the formula for finding the chemical shift, and with that formula only we have solved this question and getting the answer as 6 ppm. Now coming to the next question, that is, which of the following organic compound with the molecular formula C3H6Cl2 exhibits only one signal in the proton NMR spectrum? So four molecules are given: 2,2-dichloropropane, 1,2-dichloropropane, 1,3-dichloropropane, and 1,1-dichloropropane. So here, one among these will be exhibiting only one signal in the proton NMR spectrum. All these compounds are having the same molecular formula, that is C3.
E2-dichloropropane.
Which one?
2,2-dichloropropane.
Two.
First one.
Yeah, 2,2-dichloropropane will be having just one signal in the proton NMR spectrum. So we can see why it is so. So for that we have to draw the structure. Okay. CH3, CH3, hydrogen, Cl, Cl. 2,2-dichloropropane. Sorry. I have drawn an extra hydrogen. So this is the structure of 2,2-dichloropropane. So in this case we are having two different sets of CH3, but since they are present in the same chemical environment, because of the plane of symmetry, these CH3s will be identical, and hence they will be exhibiting only one signal in the proton NMR spectrum. Here only one signal will be coming in the proton NMR spectrum. And now when we consider the other cases like 1,2-dichloropropane, 1,3-dichloropropane, 1,1-dichloropropane, etc., how many signals will be coming, that we can see. So 1,2-dichloropropane, Cl, Cl. So this is 1,2-dichloropropane. So here the CH2 will be there, this CH will be there, and this CH3 will be there. Okay. So all these hydrogens, this can be labeled as A, B, C. So these will be in different chemical environments, and because of that they will be exhibiting three signals. Right? This is the case of 1,2-dichloropropane. Clear? Since this is
Yes,
not
ma'am.
a symmetrical molecule and all the hydrogens are in different chemical environment, so they will be exhibiting three separate peaks, where this will be of two protons, one proton, and three protons respectively. And when we consider the case of 1,3-dichloropropane, so this is 1,3-dichloropropane. So here Okay, so these, if we are labeling it as HA, HB and HC, thus A equal to C because of the symmetry of the molecule. So hence these four protons HA and HC, that four protons will be coming as one peak, and this HB will be coming as the second peak. So in the case of 1,3 dichloro-propane, you can see two signals. HA equal to HC, so that will come as one peak, and HB will come as the second peak. Hence, in the case of 1,3 dichloropropane, you will see two signals in the proton NMR spectrum. And if we consider 1,1 dichloropropane, if we consider 1,1 dichloropropane, 1, 2, 3, Cl, Cl. So here hydrogen will be there. So here all the hydrogens, they are in different chemical environments. So here you can see 1, 2, 3, 3 signals. In the case of 1,1 dichloropropane, we will be seeing 3 signals. Clear? So here 1 signal, 3 signal, 2 signal and 3 signal. So according to the question, which of the following organic compound with molecular formula C3H6Cl2 exhibits only one signal in the proton NMR spectrum? So the right option will be option A, that is 2,2-dichloropropane. Is it clear?
Yes, ma'am.
Okay. Now coming to question number 15. Predict the correct order of increasing chemical shift for the labeled hydrogens in the 1H NMR spectrum from smallest to highest delta value. So this blue labeled hydrogens, their chemical shift value order you should be telling.
Option 3. C.
Option 3. That is 2, 4, 3, 1. Okay. Option C will be the right answer. So what is the reason for that? Hmm? What will be the
And 2 and 4, there is a electron donating groups like O and Cl. They will donate the group, so electron density will increase. So it will be more shielded.
No, we are asking for if it is more shielded, then it will be coming at lower chemical shift value, right? So
Yes.
here we should be considering the electronegativity factor. So if electronegative atom is present next to a CH, like next to a proton, that or CH2 we are considering, so that electronegative atom will be pulling the electron pair like from that CH2. So the electron density around it will be lesser, and because of that it will come at a higher chemical shift value. It will be deshielded and it will be coming at a higher chemical shift value. So when we are considering oxygen and chlorine, oxygen is greater electronegative atom than chlorine, and because of that, this 2, it is having higher chemical shift value than 4. And in the next case, that is 3, this atom is not very adjacent. This CH2 is not adjacent to that of Cl. It is one CH2 away from that. And because of that, that electronegativity, that pulling of electron, it will be felt lesser because of the distance between this electronegative atom and the CH2 we are considering. Okay. So here, as electronegativity of atom present increases, it reduces the electron density around the nucleus or atom, and because of this reason, the atom or nucleus will be de-shielded. There will be no shielding of electrons, de-shielded, and hence they have greater chemical shift. So if we are considering oxygen and chlorine, electronegativity of oxygen is greater than chlorine, and because of that reason, this CH2O, CH2CH3, this proton will be experiencing greater chemical shift than this Cl, CH2, CH2, CH3. Okay. And here we will be considering the distance between the electronegative atom and the CH2 that we are considering, or the proton that we are considering. Since the distance is greater, so it will be not experiencing that much pulling of electron, and because of that, it will be having lesser chemical shift compared to 4. And here in the case of 1, there is no electronegative atom present, so it will be having the lowest chemical shift. Is it clear? Okay. So the right answer is option C, that is 1 less than, 3 less than, 4 less than 2. Now coming to question number 16. The products of the following reaction are. So here, this is a Friedel-Crafts alkylation reaction, and they have provided 4 options, A, B, C and D. And here 2 products will be forming, one major product and one minor product. So both of the products you have to identify.
Option A.
Major product is A, minor product is C. No. So like here in Friedel-Crafts alkylation reaction, so the intermediate forming will be a carbocation. So we have to consider about the stability of the carbocation while carrying out the Friedel-Crafts alkylation reaction. If it is less stable carbocation, it will try to become a more stable carbocation by some sort of rearrangements.
Ma'am, is it option D?
Option D. Major product is B and minor product is A. Yeah, that is the right answer. So we can see how it is happening. So this is our alkyl partner. CH3. Okay, so in the presence of AlCl3, this will bond and it will be removed as AlCl4 minus, leading to formation of this carbocation. Okay, but this is a primary carbocation, right? So primary carbocations are generally unstable. So what will happen? A 1 to proton shift or 1 to hydrogen atom shift will be taking place. This will shift to this position, leading to formation of a stable tertiary carbocation. Okay, so this is the reactive intermediate in this case. Then it can react with benzene, leading to formation of CH3, CH3, CH3. Here a positive charge will be there. Cl minus will abstract the proton, neutralize the positive charge, and this will result in the formation of the major product. Okay, so this will be the major product that is formed. Clear? So this is the major product that is formed, and how the minor product is forming. This primary cation will be reacting with the benzene and it will result in the formation of the minor product. So the instability of the carbocation is the reason why here the 1 to proton shift is taking place, 1 to hydrogen shift is taking place, and that is the reason why we are getting two products, CH3. This is the other carbocation. So the benzene can attack this carbocation, leading to CH2, CH3, CH3, and Cl minus will abstract the proton, and it will result in the formation of this minor product. Okay, is it clear how the major product and minor product is forming?
Yes, ma'am.
In this case, tertiary carbocation, it is stable. It will lead to formation of the major product. So 1 to hydrogen shift is taking place here. Okay, so in this case, one second. So in this case, the major product will be B. This will be the major product and A will be the minor product. Option D is the right answer. Clear? Okay. Now coming to question number 17. The major product of the following reaction is. Okay, what is the doubt?
B.
Option B.
Ma'am, option B.
A, B, C, D. For avoiding confusion. So, which is the right answer?
C. Ma'am, C.
Option C.
C.
Yeah. And intramolecular Friedel-Crafts acylation reaction will be taking place here. Okay. So 1, 2, 3, 4 on fifth carbon double bond of Cl. So let us see the mechanism. One, two, three, four. Double bond of Cl. This is our substrate. In the presence of AlCl3, this will coordinate with AlCl3 and this oxonium ion will be forming after removal of AlCl4 minus. 1, 2, 2, 3, 4, O plus. Positive charges on oxygen, okay? Now, the benzene, this double bond can go and attack on the carbon atom, utilizing the positive charge on the oxygen atom. So, how many membered ring is forming? So, 1, 2, 3, 4, 5, 6, 7. 7 membered ring will be resulted. One, two, three, four. 1, 2, 3, 4, 5, 6, 7. And here it will be double bond O. Okay. Then Cl minus can abstract this proton and it will result in the formation of the final product. One, two, three, 4, 5, 6, 7. So this will be the final product that is forming. Clear? It is an example of intramolecular Friedel-Crafts acylation reaction. Clear, right?
Yes, ma'am.
Okay. So option C will be the right answer in this case. Now coming to the next question. Choose the correct reagents for the following reaction. So on benzene, when we are treating with some reagent and AlCl3, we will be getting this as the final compound. So what are the correct reagents for that?
Ma'am, option A. Sorry, ma'am. B. B.
Ma'am, option B.
Option?
Option.
B, ma'am.
Ma'am, B. B.
Okay. You people are considering this will be the right answer, right? Okay, we can think, since alkyl group is only coming, we will be thinking that uh, Friedel-Crafts alkylation reaction is taking place. But we have to consider this is 1-chlorobutane. So this is 1, 2, 3, 4 Cl. 1-chlorobutane, and it in the presence of AlCl3, it will lead to formation of a primary carbocation. Right. This primary carbocation is not stable. Primary carbocation not stable. So what will happen? Proton will be shifting. A 1 to hydrogen shift will take place, and it will result in the formation of this. Better to draw like this. One second. This proton will shift here, and it will result in the formation of stable secondary carbocation, which will be reacting. So here there are chances for formation of multiple projects, multiple products, and this whatever resulting from this primary carbocation, it will be minor product. So this cannot be the product, and anyway 1-chloropropane can be ruled out since there are 1, 2, 3, 4 carbons. Now if we are treating with butanoyl chloride, that is 1, 2, 3, 4, 1, 2, 3, 4, double bondo Cl. 1, 2, 3, 4, double bondo Cl. This is butanoyl chloride. So Friedel-Crafts acylation reaction possibility is there now. So what will happen? It will coordinate with AlCl3. This will leave upon pushing this oxygen lone pairs, leading to 1, 2, 3, 4. Sorry. Leading to formation of 1, 2, 3, 4. Acylium ion will be forming, and it will undergo Friedel-Crafts acylation reaction with benzene, leading to formation of 1, 2, 3, 4 this product. Now in the presence of KMnO4, what will happen? It will undergo oxidation and lead to formation of benzoic acid as well as 1, 2, 3 propanoic acid. Okay, it will react with KMnO4 leading to oxidation, and it will form benzoic acid and CH3 CH2 COOH. This will be forming. But when we treat it with hydrogen palladium carbon, it will selectively reduce this ketone, leading to formation of this alkene. Okay. So for getting this as the major product, you have to follow this two-step sequence. That is a Friedel-Crafts acylation reaction with butanoyl chloride and AlCl3, followed by an H2 palladium carbon reduction, and it will result in the formation of this as the final product. Clear?
Yes, ma'am.
Okay. So option D is the right answer in this case. Now coming to question number 19. The correct order of rate of bromination for the following benzene groups is. So just a clue that for electrophilic aromatic substitution reaction to take place, the benzene ring should be electron rich. then the reaction will be taking place at a faster rate. Okay. So if some electron donating groups is present in the benzene ring, then it will make it more electron rich and the rate of the reaction will be faster. And if an electron withdrawing group is present in the ring, so because of the electron withdrawing power of that ring, the benzene ring will be experiencing less electron density, or it will be electron poor compared to normal benzene when electron withdrawing groups are present. So that you have to consider before determining the correct order of the rate of bromination in this case.
D, ma'am.
D. So here,
Option number B.
okay. So here we, oh, oh,
Second option.
no, no,
Second.
B will be the right answer. So in this case, here in toluene, CH3 group is present. It is electron donating group by inductive effect. So because of that, here the benzene ring will be electron rich, and hence it will be having a greater order of bromination or faster rate for bromination. Then comes 2, that is normal benzene. Now when we are considering this 3, 4 and 5, in these are electronegative atoms, and nitro group is an electron withdrawing group. Here the Cl and fluorine, they can be electron withdrawing by inductive effect and electron donating by resonance effect, right? In the case of chlorine and fluorine, it can be electron withdrawing by inductive effect and electron donating by resonance effect. And this fluorine's electron donating power, it will be greater because of the better overlap between the 2p orbital of fluorine and the 2p orbital of carbon. In the case of chlorine, the overlap will be between the 3p orbital of chlorine and 2p orbital of carbon, and because of that the overlap will not be that facile, and that resonance effect will be less prominent. Okay. So that is why after 1 2, then the greater rate will be coming for fluorinated benzene. 5, then comes 4, and the least order of bromination will be for 3, that is this nitrobenzene. Is it clear?
Yes, ma'am.
Okay. So option B is the right answer in this case. Now coming to last question in the session. Which among the following compounds will not react under the standard Friedel-Crafts alkylation reaction condition?
A. First one.
A.
What is the
Yes,
reason?
ma'am.
Carbocation will be extremely unstable.
Yeah. So here, uh, in the case of this compound, after treatment with AlCl3, it will result in the formation of this carbocation, which is a vinylic carbocation, and this carbocation is unstable. So it will not undergo Friedel-Crafts alkylation under normal condition. In the other cases, here it will result in the formation of a secondary carbocation. Here secondary carbocation. In this case, it will result in the formation of an allylic carbocation which is stable, and in the one second, I have drawn it wrong. This is This is an allylic carbocation which is stable, and in this case, in the presence of AlCl3, it will form the secondary carbocation. So out of this four, this vinylic carbocation is much unstable, and because of that reason, the Friedel-Crafts reaction will not be taking place under standard reaction condition. Okay, so answer will be option A, that is, this will not undergo Friedel-Crafts reaction under the standard reaction condition. Clear?
Yes, ma'am.
So this was all for today's lecture. So hope all the questions are clear. If you are having any doubt on any questions, you can ask now. If everything is clear, then we can wind up today's session. We can meet next Sunday for discussing week 2 assignment questions. So thank you all for joining.
Thank you,
Thank you,
ma'am.
ma'am. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank
Good day, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Good day, ma'am.
Thank you, ma'am. Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.